So, last time we talked about Go's fundamental types. Now, we're going to level up. We're going to explore how Go actually structures collections of data, and we're not just looking at the what, but really the why behind its whole philosophy of keeping things simple and fast.
And this quote? It just hits the nail on the head. Go isn't about giving you a million different ways to do something. Nope, it's about providing a small, super powerful set of tools that are efficient, easy for computers to parse, and, most importantly, easy for us to read and maintain.
So today, we're diving deep into Go's 4 key composite types. We've got the rigid but foundational array, the super flexible slice, the handy map, and a custom blueprint, the struct. Let's kick things off with the foundation.
Okay, let's start with the most fundamental building block for sequential data in Go, the array. You can really think of it as the bedrock that more flexible structures like slices are built on top of.
So what is an array? Well, it's just a numbered sequence of elements, and they all have to be the same type. But here's the kicker. The one thing you have to remember, its length is baked right into its type. That means an array declared as 5int can only ever hold 5 integers. This makes a 5int and a 6int totally different incompatible types in Go.
And that leads to a really critical point about memory. Arrays in Go are value types. What does that mean? It means when you assign an array or pass it to a function, you're not just passing a reference, you are creating a full-blown copy of all its data. It's like photocopying an entire book instead of just sharing a link to it. This is great for keeping data separate, but you can see how it could get inefficient with large collections. And it's a huge contrast to how slices work.
Okay, so if arrays are so rigid, how do we handle collections that need to grow or shrink? Well, that brings us to the slice, the flexible, powerful workhorse you'll be using pretty much all the time in Go. Now, this is probably the most important concept to get right about slices. A slice is not the data itself. Think of it more like a lightweight little header or a descriptor that just points to a segment of an array that's hiding under the hood. This header contains just 3 things: a pointer to the start of the data in that array, the length of the slice, and the capacity of that underlying array.
So how does this all play out in practice? Let's break it down. First, we use the make function to create a slice, giving it an initial length and capacity. Then, we use the built-in append function to add new elements, which increases the length. Now, once that length tries to go past the capacity, Go handles the magic for us. It automatically allocates a brand new, bigger array and copies all the old elements over. This gives us that dynamic resizing we want, but in a really predictable way.
And this is the perfect summary. It's as simple as that. An array's length is set in stone, part of its type. A slice's length can change whenever you need it to at runtime. That's exactly why you'll see slices used almost everywhere in Go. Even though, remember, there's always an array backing them somewhere.
Okay, now for a type that you've definitely seen before, but it has a really close relationship to slices, the good old string. In Go, a string is, under the hood, just an immutable slice of bytes. And immutable is the key word there. Once you create a string, you cannot change it. This actually makes them really safe to pass around in your program. If you do need to modify a string, you just convert it to a slice of bytes, a /byte. And for correctly handling characters from all the world's languages, you'll convert it to a slice of runes, where a rune is just Go's special name for a single Unicode character.
We've covered data that's in a sequence. Now let's switch gears and talk about associative data with Go's powerful and simple key value store, the map.
A map is basically Go's built-in hash table. If you're coming from other languages, you might know it as a dictionary or a hash map. It's just a super efficient way to associate a key with a value. The big thing to remember is that maps are unordered. You can't rely on the order when you loop over them. The keys can be things like strings or integers, and the values can be pretty much anything you want. Now here's a classic Go pattern that you'll see everywhere. It's called the comma-oak idiom. When you try to get a value from a map, you can actually get 2 things back: the value itself and a Boolean, which we usually call OK, that tells you if the key was even there in the first place. This is awesome, because it lets you tell the difference between a key that has a 0 value, like the number 0, and a key that just doesn't exist at all. It's a perfect example of how Go prefers explicit, safe code instead of throwing errors. So with maps, Go gives you this simple tool for key value data, but it's combined with these built-in patterns for safety. Just one little gotcha to remember: a map's 0 value is nil, so you have to initialize it with make before you can start adding things to it.
All right, finally, we come to the most powerful tool for creating your own custom data types in Go, the struct.
A struct, which is just short for structure, is a way to bundle different pieces of data together into one single logical thing. Each piece of data, which we call a field, gets its own name and its own type. This lets you model real-world things. So, for example, a user struct might have a name field that's a string and an ID field that's an int, all bundled together.
A really cool feature of structs is something called tags. These are basically little optional notes you can attach to your fields as strings to provide some extra information. The most common use for this is for serialization, like telling the JSON package what to name a field when you're converting your struct into JSON. It's a super simple but really elegant way to add context right where it's needed.
Now here's where Go's philosophy really stands out. Go completely avoids those complex inheritance chains you see in other languages. Instead, it prefers simple composition, using a feature called embedding. So if you embed a user struct inside a manager struct, all the methods on user, like maybe has permission, become directly callable on your manager. It's a really clean and explicit way to reuse code.
And this is a great way to think about it. In Go, a method is just a function that's attached to a type. So by combining structs, which hold the data, with methods, which define the behavior, you get object-oriented programming. But it's Go's version of it. No classes, no inheritance, just simple, straightforward composition. When you really step back and look at it, all of these types, from the fixed array to the flexible slice, the key value map, and the custom struct, are how we model our world in code. They are the fundamental building blocks that let us turn raw data into meaningful, structured information that our programs can actually understand and work with.
So we've covered how to build the containers for all your data, but now what? How do you make decisions, repeat actions, and organize all your logic? Well, that leads us right into the fundamental control structures of the language.
And in our next explainer, we're going to dive into exactly that, controlling the flow of your program with conditionals and loops, and organizing your code with functions and pointers.
This is Developer Roadmaps. Map your path. Build your career.